And I'm live, and today I have some sounds running in the background, and I will just check if it is too loud or not, and whether you guys can hear me properly or not. Mm, Okay, I am live from my side, but I cannot see it here. Just let me check. Mm, Yep, I am live, and the sound. Wait. Yep, it is fine. The sound is fine, and yep, just wait a minute. And due to some reason, today my what do you call it? Phone's camera as my webcam is working, is functional, and continuity camera. Yep, continuity camera is working today, which is crazy. And since yesterday we made this global. We made my IP address globally accessible. So, which is just crazy. And now we will begin, but there is a problem that the IP address is not DDNS. That is, since the IP address keeps changing, I had to put in a DDNS service, but the DDNS shell is not working due to some reason. So if I were to do sh duck.sh, and if I were to check my domain now, would it point to my current IP address? I think not, because it was not doing it correctly yesterday. Currently, my IP address ends at 1D03, and shit, it is correct in here. So it changed 19 hours ago. Not right now, it changed 19 hours ago. Let me see. Chrome tab. Wait on. Chrome tab. Yep, Chrome tab. L for list. Yep, it is supposed to be running. And what is in the duck.sh? My bad. Duck.sh file. Yep, it is trying to do something. Update the IPv6 address. Okay, and it is not updating the IPv6 address, but it is fine. It's fine. We can look into that later. Right now, it does point to my current IP address, which is cool. So, cd projects YouTube and /server. Server is listening on port 22. Let me check using my client code. Projects YouTube, and what is the server that the client is listening on? 80. Change it to 222. Client dot slash client, and it does work. Yep, it does work. Now what we have to do is just read the OAuth API documentation for Google, and of course the interstellar music in the background is amazing. Of course, Christopher Nolan did some amazing things, right? Hans Zimmer is the composer. hmm Right. What did we figure out yesterday? Right. Yesterday we figured out that when we want to redirect someone to authenticate themselves, right? Then we have to redirect them to a certain URL, and that URL contains information about what we want to access through their Google account. And after authentication, where they should be redirected to, and that same URL is used by Google to redirect and to send the code which we can use to access the data later, to send a sort of token to the client so that the client can access the user's data using OAuth services. Now here, CD live stream chat, CD live chat, send auth request, and attentions of file name, live chat, recover curl easy in it. Write data function and curl easy in it. Yep, this is the URL that we have to go to, and yep, this is the endpoint that we have to redirect the user to. Now our goal is to find the correct URL for our needs. I am a client OAuth ID, and what was the website? How to get OAuth access token Google Docs. This seems like it. Nope, this is just what you were reading before. This seems like it. And yep, is it it? Is this it? Yep, this is it. This is what we were doing yesterday. Is this it? Yep, pretty much. Yep. This document explains how web server applications use Google Auth API Client Library or Google Auth 2.0 endpoints to implement OAuth 2.0 authorization to access Google APIs. Let me reduce the volume only a bit. Yep. Sigmundus create assist. I have some questions to ask to ChatGPT. The OAuth 2.0 is a general set of protocols that can be implemented in order for a user to give access to a third party client to access their data on another service like Google or Facebook or GitHub. Above this general principle, auth servers and clients have implemented more specific use cases with slightly differ in the utilization of their running platform. That is, there is a slight variation for uh, that is above the root OAuth protocol. There are branches which differ from platform to platform. That is, different branch for web websites and for mobile and etc. Yes, that is a good way of thinking about it. Or what? Authorization code flow, but different platforms, web API, native application, IoT, have slightly different implementations based on their needs and constraints. These different branches or flows are designated to optimize security and usability for their respective environments. Here are the main OAuth 2.0 flows used for different platforms. Authorization code, more secure, use authorization code flow. All right, more secure for web apps with a back end used when a client. Example: a web app needs access to user data securely. The user is redirected to the authorization server, logs in, and then the client exchanges a temporary authorization code for an access token. Right, typically used when PKCE, proof key for code exchange, for added security, especially in mobile apps. Yep, everything seems fine here. Everything seems fine here. Silent. It is quite silent on the western front. It is silent on the western front. West. It is all quiet on the western front. Yeah, that is a movie. Implicit flow, legacy, used for SPA single page applications, but now discouraged. Used to be common for single page applications, SPA, where the access token is directly returned in the URL. Alright, vulnerable to attack, so it is now deprecated in favor of authorization code flow with proof key for code exchange, client credential flow. Machine to machine communication, used when a server service needs to authenticate itself, no user involved. The client directly exchanges its credential ID for an access token. Password grant flow, device authorization flow. What I want is, okay, for a web server to get access code for a user, they have to redirect the user to a URL. That URL has in query parameters the essential the accesses that the client wants, and also the redirection URL where the user will be redirected after they have logged in. Now, if the user logs in and gives the permission, the auth server needs to communicate this with the web server for which the same redirection URL is used, but how, but, uh, right, let's just confirm that much. Yes, that is correct. The redirection URL, also called callback URL or redirect URI, is a crucial part of Auth 2.0 code flow for web applications. Here is how it works. Web server redirects user to authorization URL, right? The web server, auth client, constructs a URL and redirects the user to the authorization server. Example, Google, GitHub, Facebook. This URL contains query parameters including client ID, redirect URI, response code, response type equals code, scope, state, code, challenge, if using this, right? And it looks something like this. User logs in and authorizes. The user logs in to the authorization server and approves the requested permissions. If successful, the auth server redirects the URL back, the user back to redirect URL, including the authorization code. How web server exchanges the code for an access token, right? Client code this author is yes, but this is step. Uh-huh. How is the redirection URL used for sending code back to the web server? Uh, since it is a since it is a endpoint, since it is an endpoint, uh, here the auth server does two things with the same URL. It redirects the user to that URL. That means that the user browser will send a GET request to that URL, to that endpoint, and receive an HTML file that will be rendered, and the auth server also sends a post request, that makes sense, a post request to that same endpoint to send the access token. Let's see, is that correct? Actually, the redirection URL is only used for the first part, redirecting the user with the auth code via GET request. The server to server request exchanging the code for an access token happens separately and does not include the redirect URL. First, use of redirect URL, redirecting the user with the auth code. What does it mean with the auth code? Oh, is that it? Shit, in the query parameters. Okay. The auth code will be in the query parameters of that redirection URL. All right, all right. Okay, so at that endpoint, I can query the query parameters, and right, I can query the query parameters. Mm-hmm. That makes sense. The browser makes this request, and your server handles it by extracting the code and displaying a response message. Okay, that makes sense, does it? But the code is in the URL. Ah, that makes sense, I guess, because Google knows to whom the to whom the user who the Google knows for which client ID the user has given access to. So if someone else were to use that same access code to get a token, they would be refused to do so. Now, I have to redirect the user. Yep, make the redirect URL. Yep. That actually makes sense. And yes, just first of all, let's just make a redirect URL. Redirect URL where the user will be redirected, right? And redirect client page. I have to add a client, which is my own IP address. And I hope, oh shit, it is stuck. It is actually stuck. This is horrible. Interstellar music in the background. It's crazy. Hmm. Yep, and I hope I don't get copyrighted. I guess I won't. Hans Zimmer is a nice man. I hope. Well, that doesn't mean that he would just give access to his art to everyone. It is up to him. He is the owner. Live chat display. Add secret. What is secret? Shit. If you are in the process of changing the client secret, you manually rotate them without downtime. Shit. Something just got added. Add secret added. Something. Disable. Yep. Disable. Whatever it was. Disable. Delete. Yep. Delete. Whatever it was. Client secret creation date. Data access verification center branding audience. Does audience mean who can make internal, external test publishing? Um, what I'm trying to do here is add my laptop's IP address to the list of redirect URLs. Okay, Google endpoint. Yep, this is what I want to hit with client ID, right? Client ID equals this. Yep, client ID equals this. Then redirect URI, right? URI. Yep, URI. Then response type. I'll say code and response type equal code, and then scope, let's say I can just use some scope which they have written in here. Any example scope would be fine. Test scope. What can the scope be? Scope can be quite a few things. Incremental space delimiter, telling the resources that the user wants, that the server wants. Scope. Yesterday I used the scope that ChatGPT wanted, and let's do the same thing today. Log out. Yep. And now log in, and I will see the redirection URL that ChatGPT sends me over to. Yep, this is it. And in here, you see I have everything here. Here response type is code, which is what I have chosen, and ID is also here, client ID, which belongs to ChatGPT. Then I have a redirection URL, which is openai.com, auth.openai.com, API accounts, call fallback, and then scope. Scope is this OpenID 20 profile and email. Copy, and do I see the same scope type in here? Yep, there is percentage and stuff, right? Which is, I don't know, right? Email ID, and what else do I have to add after scope? I guess scope is the last required parameter. Yep, I don't have to write any other. All I have to do is given the redirection URL, server is listening, and let me change my server to listen to HTTP. Server.c 80, and if I were to listen on HTTP on port 443, I would get an encrypted message, but since I'm not using any decryption techniques, I wouldn't be able to decrypt it. Client server. I'm now listening on port 80, and if I were to say equals http // raghav dot duckdns.org, will this work? Copy and paste. And error, yep, you cannot read because redirect URL mismatch. If I am the developer, here is flow name equals gen redirect URL mismatch. So how do I add redirection URLs to the list of redirection URLs that I can add to? It says that from somewhere in here I have to do that, but from where? And why is this website so laggy? Overview, no project, 3 hours, 7 hours, no data is available. Users, errors. Yep, there is one error. Live chat display. By clicking at it, I just clicked it. Nope, I don't see it. Expand chart legend. Yep, what is the error? Shit. Data access clients. It has something to do with this. If I do create, no, I don't think create client would, let's say web app, then the name on the screen, authorized JavaScript. Okay. So there must be some similar setting in this. Edit, can I not edit? Nope, I cannot. Let me just delete this one then. Client ID for desktop. Yep, delete this. Shit, it said something about 30 days or something. This is a web application. What is it? It is not Chrome extension, Android TV, desktop app, similar to desktop app. something similar. Let's just say web application because that is what I'm going to use for OAuth. Live chat display, right? The domain of URL you add below will be automatically added to your OAuth content screen as authorized URLs. Okay, with requests from a browser. Nope, nothing. Let me do any and redirect URI. HTTPS. Can't I use HTTP? .dns.org. It has to be HTTPS. But it is not. It is not HTTPS. It is not. Let me just put an S there and make my server just randomly listen on port number 443, which I suppose is the port for HTTPS requests. Right, it is listening on port that, and let me use Postman to check if it is actually listening on there. Mundiopius, Opus, Opium War. Crazy. HTTP H national dot dns.org. Ah shit. Fucking fuck. OpenSSL. Right, I did receive something. Connection accepted. Request sent up. Request is empty. What am I using to print the request? If I'm using printf, then I would have to change it. While yep, printf. Right, I am using printf. I'll have to change it because I am using something else. Because printf stops printing characters when it sees a null character, and since the request is in an encrypted form, it is more likely to contain a null character very early, and thus nothing is being printed. For int I equals 0, I less than buffer dot. Wait, what is n? N is n equals read that, and wait, what does n return? I was printing the buffer, right? I was printing the buffer. This is the server and size of buffer, right? And buffer is 1024 characters long. Wait, that is the input range that I'm taking. Okay. Let's then do the backlog. define buffer size 1024. Buffer size, and here I'll print the whole buffer size, and I plus plus put char buffer n, not n, I, right, and of course semicolon, prime suspect, and at the end put char 10, which is new line. Lang server.c.slash server, it is listening on port 443, and it will not send a proper request back since it is encrypted cancel. It is still sending the request, it seems. I haven't gotten anything in here, and yep, jatanraghav.duckdns.org, right, and that is encrypted. Can this is crazy. HTTPS. Where is this? Okay, let's turn this thing off. Much better. So that is HTTP. I want something for HTTPS. Yep, HTTPS RFC. Is the music ending? It will end at some point. HTTP. I want no RFC for HTTPS. HTTPS RFC. Yep. Okay, there is HTTP for over TLS. This memo provides information for the internet community. It does not specify an internet standard of any kind. Distribution of this memo is unlimited. This line, just this line, distribution of this memo is unlimited. It is very beautiful due to some reason. Abstraction. This memo describes how to use TLS to secure HTTP connections over internet. Current practice is to layer HTTP over SSL, the predecessor to TLS, and distinguishing secured traffic from insecure traffic by the use of different server port. This documents that practice using TLS. A companion document describes a method for using HTTP TLS over the same port as normal HTTP. Implementation for HTTPS. How can I use HTTPS? Shit. HTTP version this. Now I can turn the dark mode on. RFC 9114, RFC 9114, and now I can turn off the dark mode. Yep, that is long, and this seems like it. Wait, why don't I see any documentation for HTTPS? Is there a separate protocol called HTTPS, or is it or does the S at the end only specify another version of the HTTP protocol. The S at the end doesn't indicate completely separate protocol, but rather an extension of the HTTP with encryption. Breakdown: HTTP Hypertext Transfer Protocol is the standard protocol for transferring data between client browser and a server. HTTPS, HTTP Secure plus HTTP plus Transport Security Layer TLS encryption. The underlying HTTP protocol remains the same, but the addition of TLS, formerly SSL encryption, data is secured from eavesdroppers authentication, verifying the website's identity. Integrating integrity data isn't altered in transit, so HTTP isn't a separate protocol. Okay, okay, okay. Mhm. For communication over H HTTPS, for communication over HTTPS, a client has a URL for a server. The client sends a request to the server. The client sends a request to the server, which contains to the server at port 443, which contains the client's public key, which is just a string. Uh, at the server, there is a program running which is listening on port 443. When it gets such a request, it extracts the client public key, finds the appropriate response for the request uses the client's public key to encrypt the response and sends back the encrypted response to the client. The client, on receiving encrypted response an encrypted response, uses its private key to decrypt it, and see the actual response. I guess that is correct. Oh, fuck, not exactly. If the screen is not stuck, and then there was life. Not exactly. The process you described resembles public key encryption but doesn't fully capture how HTTPS works. Let's go. Wait, I saw an RFC which I actually have here printed out. It is RFC number 1180, which specifies TCP over IP communication, and it is more of explanation than definition. And it is amazing. Like, I have not read it right yet, but I will, maybe even today. client sends a request to the server. The client browser initiates a connection to the server using HTTPS port 443. However, the client does not send its public key in the request. A TLS handshake establishing a secure connection before any actual data like HTTP request response is exchanged. The TLS handshake occurs. Okay, TLS RFC latest transport layer security. Yeah. That is it. This documentation specifies version 1.3 of Transport Layer Security TLS protocol. TLS allows client-server applications to communicate over the internet in a way that is designed to prevent eavesdropping, tampering, and message forgery. This document updates RFC this and this and obsoletes this and this and this. This documentation also specifies new requirements for TLS 1.2 implementation. Okay, that is good. That and pretty long. How long is it? It's PDF 160 pages long. It is fine. TLS. This is pretty detailed, and with that is TLS. Then latest HTTP RFC. Latest HTTP RFC. It is 1.1. Wait, there is this RFC which is later than that, and for the same version. Let's see. And abstraction. The hypertext transfer protocol is a stateless application protocol for distributed collaborative hypertext information systems. This document specifies the HTTP 1.1 message syntax, message parsing connection, and related security concerns. This document obsoletes portions of RFC 3.2. This state of this. No, this is this an internet standard tracking document. Okay, and what is the PDF for this? PDF is not that long, surprisingly. Okay, and RFC number 9112. RFC 9112. RFC 9112. Shit, fuck. That is too bright. Fuck. And RFC 9114 specifies HTTP over TLS. Okay, that is cool. Okay, now I know what I have to read and understand, of course. Then there is no point in reading if I don't understand it. Okay, yep, I can go back to ChatGPT. So HTTPS, it turns out, is only HTTP, but it also has TLS, Transport Layer Security protocol implemented. Right, first a TLS handshake happens. The client sends a message called client hello, which includes supported encryption algorithm, cipher suits, a random generated number, client random, server hello. The server responds with server hello, which includes the encryption algorithm chosen from the client's list. Alright, so client sent a set of algorithms, encryption algorithms, and the server receives it. Server says hello, and the server chooses one of the algorithms provided by the client, and another randomly generated number, server random. The server's public key, which is part of SSL TLS certificate, secure shell. Key exchange. The client now generates a pre-master secret, a random string. It encrypts this secret using server's public key. It encrypts this secret using the server's public key from the certificate. It encrypts this secret using the server's public key. The client now generates a pre-master secret, a random string. It encrypts this secret using the server's public key from the certificate, right? The server, which the server sent in its server hello message. Then the client sends this encrypted pre-mastered secret to the server. Okay. The server decrypts it using its private key. Now both client and server derive the same symmetric encryption key using the pre-master client secret, client random and server random. The server decrypts it using its private key, generates a pre-master key, it encrypts this secret. Okay, on receiving server hello, the client generates a pre-master secret, a secret key, which it encrypts using whatever the server's public key is. The client sends this key, my bad, to the server. The server decrypts it using its private key. Now both client and server derive the same symmetric encryption key using the pre-master secret, client random and server random. At this point, both client and server have established a shared symmetric key which they will use for encryption. Secure data exchange. Using symmetric encryption, now that a secure channel is established, the actual HTTP request and response happens. From this point forward, encryption is done using a symmetric encryption algorithm, example AES. The server encrypts the HTTP response with this symmetric key and sends it to the client. The server encrypts the HTTP response with this symmetric key. Encrypts the HTTP response with this symmetric key and sends it to the client. And the client decrypts it using the same symmetric key. Why not just use public key encryption for everything? Public key encryption, asymmetric encryption is slow because of its computational complexity. Okay, so public key encryption is one way and symmetric encryption is another way. For symmetric encryption, they first do a TLS handshake, which establishes a method for both of them to encrypt and decrypt messages in a common and quick, faster way. And so that when they make some other secure connections at some other time, they will have to handshake again. But the happy thing is that the key is randomly generated. So even if it is leaked, it doesn't matter because the next time you connect to a HTTP server, you will be using something else. Instead, it is only used in TLS handshake to exchange a symmetric key securely. Once the symmetric key is shared, all further communication is encrypted using fast symmetric encryption. Alright, so all of this is like actually written in code and happens in real time whenever I send or you send any request to anywhere using HTTP, which is fucking crazy. Summary of HTTP encryption flow. TLS handshake. The client and server agree on an encryption method. The client encrypts a secret key using the server's public key, right? The server decrypts it using its private key. Both generate a shared symmetric key. Okay. Alright. They first agree on an algorithm. Okay, so we have why we have green, no, we have client and we have a server, which is crazy, which is like actually fucking crazy. So when they want to communicate using HTTPS, this is what happens. The client generates, due to some reason, a random key. The client generates a list of algorithms: algorithm 1, encryption algorithm, algorithm 2, and algorithm 3, and some stuff, and sends it to the server. The server chooses one algorithm, let's say this, along with its public key, public key, and sends both of these back to the client. The client uses the public key provided by the server, public key of the server, to encrypt a random number, to encrypt a random number, and sends it back to the server. The server sees the random number and decrypts it. Wait, is my camera off? Nope, it is working. It's fine. It might be on low battery, but I can just remove it and use my laptop camera later. Decrypts that random number using its private key, which the PRIV private key, and this random number is the key which they will be using to encrypt whatever the data they will be sharing. And the algorithm was decided by the server from a list of algorithms that was sent by the client. And this gives the key to the server. Now, maybe if someone was listening on this network, they could know the algorithm that the server and client are using to hash to encrypt the data, but they want to know the key because the key was generated anonymously by randomly by the client and then encrypted and only then sent to the server. And if someone were to intercept, they would only see that encrypted key and not the actual key, encrypted key. And the server, on receiving that encrypted key, decrypts it using its private key. And now the server has the key and it also knows the algorithm. After that, server finds the appropriate response for the first get request that it should return with. It finds the response. The server then encrypts the response using this algorithm over this key and sends it to the client. The client, on receiving an encrypted response, decrypts it using this key and algorithm. And this client has the data, and all the subsequent requests are made using just this method, which is crazy. Seems like the music has actually ended. And can you hear the music, Robert? Sic mundus creatus est. Yep, error view in console. This is a crazy error like this. Ep2, this SSL wrong version number, and this is the response that a request that I got on my server side. Why does this seem like it is encrypted? Wait, what the heck is this? Abomination. Shit, it is actually lagging. Signed to Google account. So I guess I understand a few things. So first the TLS and shake happens, which establishes an encryption algorithm and a key which only the server and the client know. And now every subsequent request and response uh, happens using this encryption algorithm and key. That is exactly it. Yes, exactly. After the TLS handshake, the client and server both have an agreed upon encryption algorithm, right? And a shared symmetric key which only they know. Now all subsequent communication, request and response is encrypted using this symmetric key. This ensures confidentiality, integrity, authentication. And now, does this TLS handshake happen over the 443 port? Does it happen over the 443 port? Yep, the TLS handshake happens over 443 port, the same port used for encrypted HTTPS communication. How it works: the client browser contacts the server on port 443 and initiates the TLS handshake. The handshake establishes an encrypted connection. After the handshake, all for the HTTP request and response happen on the same 443 port. Alright, so the server listens on port 443 and that is very low battery, and I will turn off my continuity camera when it goes down to 20%. But can I make it? I have the charger is inserted, but it does not help. It has to be in a certain orientation for it to be charging. So this is what I have. On the server, so the server listens on port 443 and determines based on the received request whether it is a request to establish a TLS handshake or to handle an encrypted HTTPS request or to handle an HTTPS request. And in case of a TLS handshake, it starts the TLS and shake process, and after getting a URL, after getting an encryption algorithm and a key for a specific IP for a specific IP address, it adds that to the global hash to some thing like a global hash table which contains the keys and goes for all the current secure connections, and if it is an encrypted request, and if it is an encrypted if it is an encrypted request. If it is an encrypted request, then it looks in the global hash table to find the algorithm and key to decrypt the message and find the appropriate response. Yes, that is the general idea. What the server does when listening to port 443 receives a request on port 443 if the ah fuck I messed up at one point. Yep. If the request is an encrypted HTTPS request, it decrypts it using the already established session key. How the server manages secure connections. The server does not maintain key for IP address directly. Instead, it uses session identifiers or TLS session tickets. After TLS handshake, the server restores the encrypted algorithm and session key in memory for the duration of the session. If a new encrypted request comes in, the server checks its session cache for matching session. If found, it retrieves the symmetric key and algorithm. It decrypts the request and processes an optimization SSL TLS session, secure layer transfer layer security. To avoid redoing the handshake every time, TLS supports session caching and session tickets. Server stores session and client stores an encrypted ticket from the server for reuse. Alright, so the server identifies the client not from their IP address but from the session key that comes with their request, but with the session key that comes with the request. Exactly. Not IP address. The session is tied to the client-server relation, not their IP address. A client may change its IP, example due to dynamic IP assignment, well network or entity, but the session key is still valid. For the current connection, the server can track multiple clients with different IPs that are using the same session via balancing or distributed setup. So what it means is I have to now set up an HTTPS request server in C, which handles encryption and all that stuff. And I'm not going to use encryption just yet, which is fucking crazy. I'm not going to get into the weeds of sending and selecting some encryption algorithm and storing the key, session ID, and stuff. How to create an HTTPS server in C. Let's see, to create an HTTPS server in C, you'll need socket programming. I want to fucking hell. Prerequisites: C compiler, code steps, socket, listen, bind. Okay, that much is understandable. Then SSL, right? Request handling, uh-huh. SSL, right? SSL shutdown. Okay, SSL TLS. All right. So first, when I get a request, I will establish an SSL connection, and then on subsequent requests, I will be using the SSL methods for writing and reading and stuff, creating a web server from scratch in C. That is a tempting title, making minimalistic HTTP servers in C in Linux. To build a simple HTTP server from scratch in C, that is an HTTP server. Mhm. Sockets and stuff. There is an app which can be used to take screenshots like this, right? Oh. Mhm. Yep, that is socket programming. Writing HTTPS. And what is a certificate? Secure shell. What is a SSL certificate? SSL is a digital certificate that serves two primary purposes: authentication. It verifies the identity of a server, of a website or server, to ensure that the server you are communicating with is indeed the one you expect. That is, it is not a imposter or man in the middle. All right. Okay, so okay, authentication. It seeing a certificate, you know that this person is the person that you want, but can't that be copied? I guess that cannot, because yes, since the client. Nah, nah, nah. Let's see. When you visit a website over HTTPS, your browser checks the server's SSL TLS connection to ensure it matches the domain SSL TLS certificate, to ensure that it matches the domain name of the website you are connecting to. It also confirms the certificate has been issued by a trusted certificate authority, CA encryption. It ensures secure connection by providing the server with a public key. Oh, it provides the server with a public key used in the TLS handshake, which helps establish an encrypted connection between the client and server. The server's public key is included in the certificate, which the client can use to encrypt data back and send it back to the server. Okay, so even if someone were to copy the client's right. So even if someone were to copy the server's certificate and show that certificate as their own, they would not be able to use the certificate effectively, because when the client sends them the key for the selected algorithm, it can only be decrypted using the server's private key, which any middleman won't have. The server's public key is included. Yep, this ensures the sensitive data like password, credit card information, etc. can be easily intercepted. Components of an SSL certificate: public key, private key is stored securely on the server, domain name, certificate authority, expiration date signature. How it works? Like how can I obtain a certificate of my own? Use a free authority like cert bot. Fucking hell. Yep. Python 3 cert bot. Okay, that is cool. And now I want to create an HTTPS server in C, for which I will have to spend some time and go onto YouTube and watch some videos, for which now I am ending the stream because I do not want to watch YouTube videos on the stream, which would be crazy. So that is it for today's C stream. And tomorrow, hopefully, well, fuck, tomorrow is holy, but hopefully we will be at and we would have created an HTTPS server.